Good morning. Today we are going to start with the next application of derivatives, which is maxima and minima. Okay, so consider any function y equal to fx. If it's a continuous function, we can draw the curve as something like this. So it will have certain ups and downs, and the point at which it changes from going upwards to going downwards, or the other way around, that is from going downwards to going upwards, is called as turning points. So there are so many turning points. This is a turning point, this is a turning point, this is a turning point, and so on. And these points at which the curve turns its direction, they are called as the points of extremum. Extremum, which means maximum and minimum. Okay, and this, the short form of maximum is maxima, point of maxima, and this is called as point of minima. Point of maxima and point of minima. Okay, so this is what we are going to deal with now. So if we observe carefully, if suppose we are talking about a point having maximum value, at which the function has maximum value in some interval. Okay, so suppose we have a point C. Okay, then corresponding to which, this is the point C, where as you can see there is a point of maximum, like the value in its immediate neighborhood is maximum. So the value of the function in the immediate neighborhood is maximum, and so we call this a point of maximum. Similarly, if C is a point here such that in its immediate neighborhood the value of the function at C is least as compared to the immediate neighborhood, then we say that this point is a point of minima or minimum. Okay, so now, so basically what we see is that, and this point now, whereas if you consider the entire function as a whole in the whole domain, whichever point gives you maximum value, see that is called as a point of maximum, whereas each individual maximum points are called as local maxima. Same way, the finally in the entire interval, whichever is the least value, like here it is the least value, this is the point of minimum, where, or we call it absolute minimum, whereas each of these points at which the value is least is called as a local minima. You will understand it better as in when we take up some problems. Okay, now how do we, so what do we see, that if C belongs to a open interval C minus h, C plus h, means within a close neighborhood of this point C. Okay, the point, x is equal to C, which belongs to the open interval C minus h, C plus h, means a close, a very close neighborhood of the point x equal to C. If fc, value of the function, is greater than or equal to the value of function at x, where x belongs to this immediate neighborhood, then we say that x equal to C is a point of local minimum. This is maximum, so local maxima. Why do we say local? Because we are seeing in the immediate neighborhood, whereas if x belongs to a small interval C minus h and C plus h, which is the immediate neighborhood of the point C, such that Fc is less than or equal to fx, then the point x equal to c is a point of local minima, as you can clearly see from the figure above. Okay, now how do we test whether it's a how do we find the points of local maximum or minimum? These are also called as extremum or extrema, points of extrema, or the points at which, obviously when there is a maxima or a minima, the function changes its direction. So these are also called as turning points and also called as critical points, and also called as points of extrema. And extrema means it could be minima or it could be maxima. So we have there is a theorem which is called as the first derivative test. Okay, it says that if f is a function defined in an open interval I, and if it is continuous in that interval, okay, then now if you just observe, before just writing down all the postulates of this, I will just explain what this first derivative test is all about. Now if you just go through the continuous curve, okay, you can see that the point of maxima is this one and this one. So what's so special about these points of maxima? The function changes from increasing to decreasing. Here also, just before this point the function is increasing, whereas just after this point the function is decreasing. Just before this point the function is increasing, and just after this point the function is decreasing. So we have x equal to c is a point of local maxima if the function changes from increasing to decreasing at x equal to c, which you can see from this figure. Whereas at the point of minima, the function is changing its direction from decreasing to increasing. Here also from decreasing to increasing, and here also it is decreasing. So what do we have? X equal to c is a point of local minima if the function changes from decreasing to increasing at x equal to c. And based on this only we have, and again if the third point would be x equal to c is a point of, it's neither a maxima nor minima, or is neither maxima nor minima if the function doesn't change, if the function doesn't change its nature. Means if it is increasing, it remains increasing. If it is decreasing, it remains decreasing. Like for example, at this point, somewhere in between the two points of extremum, here if you just see, it remains. Suppose you are taking any point C over here, then on the left also it is increasing, after the point also it is increasing. So this point is neither a maxima nor a minima. So based on this we have the first derivative test, which says that, so from increasing to decreasing means f dash x should be greater than 0 on the left and less than 0 on the right of x equal to c. And so we say that if f dash x changes sign from positive to negative as increases through the point C, then it implies that x equal to C is a point of maxima, whereas second point says if f dash x changes sign from negative to positive. What is the meaning of this? It changes from negative means decreasing to positive means increasing. As x increases through the point C, it implies that x equal to C is a point of minima. So, let us take one example of this kind and then we will take up the next result. Now, let us take up one question. Suppose we have to find all points of local maxima and local minima of the function given by, this is the example 29, okay, given by f(x) equal to x cube minus 3x plus 3. So, first step involved in finding in using the first derivative test is we have to find the critical points. So, first point is to find the critical points. Now, what are critical points? Critical points are the turning points or turning points. And what is the meaning of turning points? Where it changes the direction. And when will it change the direction? That is when f dash x is equal to 0. Okay. So, that is f dash x should be equal to 0. This we have to find. So, first of all we find f dash x equal to 3x square minus 3 equated to 0. You solve it as x squared minus 1 equal to 0, x minus 1 plus 1 equal to 0, and so we get two critical points which are x equal to minus 1 and x equal to plus 1. Now, again we will make a table similar to what we did in increasing decreasing functions, and so we write intervals, then we write f dash x equal to 3 times x minus 1 x plus 1, and then we write the sign of f dash x, and so we see the nature of the point. Okay. So, first of all let us write down. First interval would be minus infinity to minus 1. Okay. Now, what do we have? If we take a point on the, okay, first of all we take minus infinity to minus 1, then we take minus 1 to 1, and then we take 1 to infinity. And how do we check the nature? First of all we take the point lying in this interval. So, let us take it as minus 2 here, in this let us take it as 0 here, in this let us take it as 2. Now, f dash x will be equal to minus 2 minus 1 is negative, minus 2 plus 1 is also negative, which is positive, which is greater than 0. Okay. So, this is greater than 0. Now, f dash x is greater than 0. Okay. So, it is increasing. Now, here we have f dash x will be equal to, when you put 0 it is negative into positive which is negative less than 0, f dash x is less than 0 which is decreasing. Now, f dash x equal to, now here you put x equal to 2. So, what do we get? Positive into positive which is positive greater than 0, f dash x is greater than 0, and so it is decreasing. Now, what do you observe here? Here we see that on the left of x equal to 1. Now, so the what kind of point? So, type of critical point. Okay. So, x equal to 1, as you move from left to right about x equal to minus 1, we see that f dash x changes from increasing to decreasing. So, this implies that x equal to minus 1 from increasing to decreasing is a point of maxima. Now, here if you just see, on the left of 1 f dash x is decreasing, on the right of 1 it is increasing, and so it implies that x equal to 1 is a point of minima, because as we move from left to right across x equal to 1, the function changes from decreasing to increasing. So, it is a point of minima and this is a point of maxima. This is how we use the first derivative test, but we don't use it very often. We use it, mostly we make use of the second derivative test, which we will be taking up later for all our questions. Now, let us start with some simple questions of exercise 6.5. Now, which can be done by the basic of the concept of maxima and minima. So, let us see. First question, first part is f(x) equal to 2x minus 1 whole square plus 3. Okay, now we have to find the maximum and minimum values, means value of the function, not the point of. So, here we are required to find maximum and minimum values, and whenever we talk about values, we talk about the value of f(x). Okay. So, first of all, we will find the point at which the function will be maximum or minimum, and then we find the maximum or minimum values. Okay. So, first of all, let us see. We know that this is a perfect square. So, 2x minus 1 whole square is always greater than or equal to 0. Okay. You add 3 to it, it will always be greater than or equal to 3. So, it means that f(x) is always greater than or equal to 3. It means f(x) belongs to, it is always more than this. So, how do we write this? And infinity. So, the minimum value of f(x) is equal to 3. Okay. And there is, since here it is infinity, we say that no maximum value. Reason being, we can't find what is, we can't give a value to infinity. Now, what is the point corresponding to which we have got a minimum value? So, the, see, 2x minus 1 whole square is greater than or equal to 0. The f(x) would be least when this is 0. So, f(x) is minimum when 2x minus 1 whole square is 0, which is equal to 2, which gives us 2x minus 1 is equal to 0, which gives us x equal to half. So, when x is half, we get the value of f(x) is 3, which is least. So, minimum value of f(x) is 3 at x equal to 2, half. This is the answer. So, this is how you can try the second, third and fourth parts also of question number 1. Thank you.